Hello everyone, welcome to week 3 of Photonic Integrated Circuits tutorials. So I am Mukta. I work with Professor Shankar and I will be covering some of the assignment problems that we encountered in the previous 2-3 weeks. So yeah, let's begin with assignment 1. Assignment 1 uh, basically talks about all the different topics of reflection, diffraction, total internal reflection, wave propagation in the material, all the topics that were covered in the first week. So let's start with the first question. Light propagation in a waveguide is assured by, total internal reflection, total external reflection, total internal refraction, or total external refraction. So light propagates in a waveguide. So there were two conditions, right? So a waveguide should have a refractive index n that is higher than the core of the waveguide that actually guides the light should have refractive index that is higher than the cladding. So n core n clad, and we know that n core should be greater than n clad. And this condition, whenever this condition is met, then there exists a critical angle at which if the light strikes or be at if the light strikes at an angle greater than the critical angle, then instead of getting refracted into the cladding region, the light will bounce back in the same medium. And this process is so we can see that clearly that this is a reflection process. So it is reflection and it is reflecting internally, so it is called as total internal reflection. Okay. So the next question is, what is the wavelength of light in a medium of refractive index 3? So n is 3. If the free space wavelength is lambda naught is 1200 nanometer. Okay. So the relation between the wavelength in a medium and wavelength in a free space, this relation, the exact relationship can be found out pretty easily. So we know what is refractive index. So by definition, refractive index is nothing but c over phase velocity in the medium. C is the velocity of light in vacuum. Vp is the velocity of light in the medium, to be more specific, phase velocity of light in the medium. And this Vp is nothing but, we can find it if we know the frequency of light and the propagation constant. So Vp is nothing but omega over k. And then now this k, what is the k? K is nothing but 2 pi over lambda in the medium. So now you see where I am going with this, right? So if k is 2 pi by lambda medium, and from here also I can get k, right? So k will be nothing but omega over Vp. And what is Vp? Vp is c by n. So I can write as c by n. So omega n by c is k. And that is equal to 2 pi by lambda in the medium. And what is omega over c now? We know that this term here, omega over c, is nothing but k naught, right? So that is the propagation constant in free space. That is free space propagation constant. So that is nothing but 2 pi over lambda naught, that is free space wavelength, into n is equal to 2 pi over lambda in the medium. 2 pi gets cancelled. So we have lambda median is equal to lambda naught upon n. So by this relation, sorry, so from this relation we can see that uh, lambda median is 1200 nanometers 400 sorry upon 3, so that is 400. Okay. Yeah, so it's recording. Okay, so the next question is, a light wave of wavelength 1000 nanometer is directed in the xy plane at 45 degrees. Okay, they have given us the wavelength. Wavelength is lambda is 1000 nanometers and it's directed in the xy plane at a 45 degree angle. It's directed like this. We can imagine it like to be a plane wave. For this propagating wave, what is the magnitude of the k vector? Okay, so they are asking the magnitude of the k vector. So we know that the magnitude of the k vector, just like we discussed right now, is nothing but 2 pi over lambda. Since they have not specified the medium, we'll just assume it to be vacuum. Okay, so that is nothing but 2 into 3.14 upon 10 power 3 into 10 power minus 9. Oh, sorry, they are asking in radians per centimeter. So nanometer to centimeter will be -7 and then 3 is -4, I think. So this will come out to be 6.28 into 10 power 4 radians per centimeter. So that we can fill it here, 62800. Okay. Light wave of wavelength 1000 nanometers, same again, is directed in the xy plane at 45 degrees. For this propagating wave, what is the direction of the k vector? Now they are asking us the direction. Okay, so they have already told us that it's propagating at 45 degrees. So the direction of the k vector is the same as the direction of propagation, or rather parallel to the propagation direction. So so then now we already know the magnitude of the k vector. So what is k vector? K vector is magnitude of k cos theta x cap plus magnitude of k sin theta y cap. So all I'm doing here is, so if I have a okay, let me draw it here. If I have a Cartesian coordinate system and my k vector is 45 degrees, so then what is the x component? The x component of k vector is magnitude of k cos theta, right? And the y component is k sin theta. This is y, this is x. Okay, so I just wrote the components and the corresponding directions or unit vectors. Yeah, so in for cos 45 degrees, what is cos 45 degree? Cos 45 degree is We can just take the value from the net. So yeah, cos 45 degrees 0.707 into the K magnitude, that is 6.28 or 62800. So we'll do it into 62800. This 44406. That comes out to be 44406. Since cos theta sin theta are same, so we can take it outside. X cap plus y cap. For 45-degree angle, both cos and sin are same. Right. So we just need to write this here. Since they're asking in radians per centimeter, we can just write the number and yeah. The refractive index of the core material in a waveguide is dash than the cladding, is greater than the cladding. The energy of a photon of wavelength 1200 nanometer is, okay, so energy is nothing but, energy we know is h times nu, right? Or we can write it as hc by lambda. So now it's just a matter of substituting in the formula. What is h? H is 6.626 into 10 power minus 34. C is 3 into 10 power 8 by 1200 nanometers, 1200 into 10 power minus 9. So that comes out to be 1.656 into 10 power 19, 10 power minus 19 joules. But now they are asking us it in electron volts. So then we just divide it by the charge of an electron, that is 1.6 into 10 power minus 19. 10 power minus 19 cancels. And so it will be 1.656 divided by 1.602. Into 10 power minus 19, 10 power minus 19 will cancel that many electron volts and comes out around 1.033 electron volts. Okay. Interference of light can be explained by using ray theory. Yes or no? So light interference basically means that if I have okay, so let's understand it in terms of Young's double slit experiment. So if I send light through both the slits at the same time, so the light has to be coherent, same single wavelength coming from the same source, and if I send light through the two slits, then I see a pattern of dark and bright fringes. So this phenomenon is interference. So can we explain it by using ray theory? So if I just have a simple ray theory, what will I expect? I'll expect that the light goes straight and hits at the screen at 2 points, right? So the rays will only travel in straight lines, or if it's coming at an angle, say the light is falling at the slit at some angle, then it should go and hit at some other place. However, we expect only 2 spots on the screen, but when we are talking about interference, we see a series of bright and dark fringes. So to explain this, we need to move towards the wave picture of light. So in the wave picture of light, so when the plane wave hits the slits, it forms such semispherical waves, and when they add up or subtract based on their phases, we get a bright and dark fringe pattern on the screen. So it's like if I have a wave, say say this is the position axis or the time axis, any axis, and intensity or the field. Okay, and if I have another wave, and the magnitude of the electric field goes, so you see that it's not exactly in phase, right? So it is slightly shifted. So when these two are present at the same location, the resultant waveform will be a sum of both of these. So at some places uh, where they are 180-degree out of phase, there might be a distance. So the resultant intensity would be, some places there will be constructive interference, some places there will be destructive interference, like that. So based on the phase difference between the two electric fields, whenever we have a 180-degree phase difference, then the crest will overlap with the trough, and the net intensity will drop down to 0. Okay. So to explain interference, we need wave theory. So no. What is the real part of refractive index of a material with complex susceptibility of so much? So they have given us chi. Chi is 12.7 plus I times 0.49. So it's a complex number. Okay, so once we have chi, how do we find out the refractive index? So we had learned the susceptibility as a quantity that relates the electrical polarization vector to the electric field vector. So polarization P of omega is epsilon naught times chi of omega times electric field vector. Right. And we had also learned about electric displacement, right? So what is displacement? Displacement is nothing but it quantifies how the field behaves inside a material. So it's the permeability of the material times the electric field. So that is nothing but, permittivity of the material times electric field. That is nothing but permittivity of free space times electric field plus the polarization. So right. So now this epsilon is nothing but we can write it as relative permittivity times the permittivity of free space is equal to, now substituting for P from here, I can write this as epsilon naught E 1 plus chi. Correct. This I can cancel. So my relative permittivity is 1 plus chi of omega. Now how is relative permittivity related to refractive index? Okay, so this is easy to see. Where do I write? I write in a different color. So my refractive index is nothing but C over Vp, just like we discussed just now. What is C? C is 1 by root mu naught epsilon naught, and Vp is 1 by root mu epsilon. So n is nothing but the root of epsilon by epsilon naught. That is nothing but relative permittivity. Correct. So from this I can write n is equal to root of 1 plus chi of omega. So now using this equation I can easily find out what is the refractive index given the permittivity, right? So now my refractive index will be nothing but root of 1 plus chi of omega. That will be root of 13.7. 12.7 plus 1 is 13.7 plus I 0.49. Now the next task is to find the real part of the refractive index. For that we use an identity uh, that is common in complex numbers. I'll write it down. Root of a plus ib is equal to plus or minus bracket root of a square plus b square plus a upon 2 whole thing root under root plus I times b by mod into root of a square plus b square minus a by 2. Okay, so we only need the real part. So we will be only computing this, and if we do it for and like by substituting for a as 13.7 and b as 0.49, we will get a number close to 3.65. So that is what we need to write here. So the real part of refractive index will be 3.65. So obviously refractive index will not be negative. So we will write the positive number for it to be physically reasonable. Okay. Change in refractive index with wavelength is called. Okay. So by definition, change in refractive index with wavelength is called dispersion. So what do we mean by change in refractive index? It means that different wavelengths of light are traveling with different speeds, or different frequencies of light are traveling with different speed in the same medium. So that results in dispersion. So if I have a pulse of spectral width, some spectral width, so based on the spectral width, so if my x-axis is lambda and y-axis is the intensity, and say my light has some width, so it's not a single frequency light, it has some contribution from the neighboring frequencies as well. Then if I send a pulse of light, so in time, if I'm sending a pulse like this through a dispersive medium, then on the other end, due to the dispersion, I will see a broadening of the pulse or a shortening of the pulse. So the pulse shape will be altered because these different wavelengths will travel at slightly different speeds. So that is called dispersion. Last problem for this assignment. Consider a 60-watt light bulb. Assume that all radiation given off is in the form of light of wavelength 650 nanometers. Calculate the number of photons given off per second. So lambda is 650 nanometers. And they have given us the power consumed by the light bulb. Power is 60 watt. Right. What does it mean? It means that it consumes 60 joules of energy per second. And now, since we know the wavelength of the photon, we know the energy of one photon. Energy of one photon is nothing but hc over lambda. Okay, so calculate the number of photons given off per second. Okay, so if the total energy per second is 60 joules and energy of one photon is so much, then how many number of photons per second is nothing but 60 over hc by lambda. And if we just do this calculation by substituting for hc and lambda, we will get 1.96 into 10 power 20 photons. Okay, so that concludes this assignment. We will move on to the next assignment. So assignment 2 was mostly just uh, factual questions, so we'll skip that. So most of the people had doubts only in assignment 1 and assignment 3. So I'll be jumping on to assignment 3 now. Right, so the first question is the phase velocity of a wave of frequency 194 terahertz. Sorry. For some reason, it's not letting me write.